Our next speaker is Danilo Lewanski, and the title is Resurgent Topological Recursion. So, Danilo, please.
Okay, good morning, everyone. Last talk, I hope you're not too tired. Thank you for having me, for this opportunity to speak. I feel I'm a little bit an outsider of this community, so I'll quickly introduce myself. I'm currently at IHES as a postdoc, the same institution as Maria. I've been visiting Geneva actually a couple of years ago, visiting the researcher Camilla Felisetti. I gave a talk there. And the main message I would like to bring with this talk is about topological recursion. So I would like to say why this is interesting to me, why this could be interesting for you, and also mention some possibilities in case you want to learn more. For instance, I'm organizing a conference about it. So I'm part of this project. It's an ERC synergy project that is called Renew Quantum, that stands for Recursive and Exact New Quantum Theory. It was, I mean, the ERC synergy is the biggest ERC grant. I was granted to Professor Marcos Marinho, together with other 3 principal investigators around Europe. So it's Maservich, Anderson, and Enach. I'm currently studying with Enach. And I mean, one of the pillars, I would say, of this project is about topological recursion, which is a relatively new method. And probably, I don't know how many of you have heard of topological recursion before. And it's very hard to give talk virtually because you cannot see the audience. But could you please add a plus in the, just type a plus in the chat if you have heard of topological recursion before? Just to have an idea of the audience. I know some of you did, but just have a proportion about how much should I give for granted and how much should I explain. All right, plus or minus. Okay, thanks. Yeah. All right, so I will try to give the gist of it and give the definition, and mostly motivated with a lot of examples and say why we believe there is resurgent behind it. So this is the main message of the talk, and there will be also one main original theorem inside it. All right, so let's look at the time. Yeah, so this is for me the big picture at the moment. So you can see here above the sea level, 3 major areas. I come from algebraic geometry originally, and then I moved to mathematical physics. But for me, the motivation is a little bit the following. You have some enumerative problem. This enumerative problem can come from theoretical physics. For instance, it could come from string theory, or it could come from some random matrix models, as you mentioned before in your the talks of this morning many times. And then it turns out that the numbers out of the expansion of the partition function that you have, or the invariance that you want to compute, they can be expressed as integrals over the moduli space of curves that you see here on the right. So you have, you're interested in some cohomological description, and you want to express the numbers as some cohomology class of the moduli space of curves integrated over MGM. And this is also very interesting from algebraic geometers, because they all of a sudden see that some particular classes in the cohomology have a privileged role because they come from some independently studied problems from physics. So this is a very interesting link. And also you can build some partition functions out of these integrals, and then often they satisfy some PDE, some integrable hierarchy, which is an infinite list of PDEs in infinitely many variables, or Virasoro algebra. Sometimes it is equivalent. And so you have some Virasoro operators that commute and then annihilates your partition function that at that point is a tau function of some integrable hierarchy. So understanding this connection between the 3 objects above the C is something interesting for me. And we are still far from clear understanding. And in general, this is very hard, that using the tool of topological recursion, we have much more reasonable probability of succeeding for the enumerative problems that can that obey topological recursion, because topological recursion gives us some geometric tools, essentially. And then, well, under the sea, there is Resurgent, and that's work in progress by many people and by the IHES synergy project, of course. So let me go fairly quickly, just as a motivation. Moduli space of curves that I would call MGN or MGM bar. It's a compactification. It's moduli space of complex compact curves of genus G with n labeled mark points. And one of the main interests in the algebraic geometry of moduli space of curves is to understand its cohomology. It's very big, so people have been studying a subring that is called tautological subring and has many nice properties. And you probably know these psi classes, which are the fundamental building blocks of the cohomology, which are defined. So you have mark points 1 to n. And then psi I, what is it? It's just the first Chern class of the cotangent bundle over the ith mark point. So you have n of them, and then you can forget mark points and push them forward. Those are the Mumford kappa classes. And then you have Hodge bundle and so on. And this turns out to have many applications in Gromov-Witten theory, string theory, random matrix models, Hurwitz theory, and so on. So let me go to the juicy part. What about topological recursion? So the formula looks a little bit intimidating if you haven't seen it before, but it's actually rather easy, and I will try to explain a little bit what are the main things to look at. So it originally arises from random matrix models. This, I think, it's something that could be interesting for you. So if you have a random matrix model, you can ask it to be stable under infinitesimal deformation of the matrix. And then you get out of the equation that, I mean, imposing that is stable, you get some equations that are called loop equations. And the first of these loop equations will give you some relation that gives rise to a curve. Sometimes it's an algebraic curve, sometimes it's not. And is what is called the spectral curve of the random matrix model. Right, so this is how topological recursion was born. People were deriving the spectral curve, and then they were running a procedure that is called topological recursion, generating from the spectral curve the correlation functions of the matrix models. So this is the initial motivation. And then there was the big realization that you actually don't need the matrix model in the first place, because if you happen to have a spectral curve, then you could just run the algorithm. And there are certain conditions on the spectral curve which are allowed. And then sometimes you just happen to have a spectral curve. You don't know what the matrix model is. You can try to derive it. Sometimes it's very difficult. Sometimes the matrix model is not there. Sometimes you have a quantization of a spectral curve. But in principle, you can just run the algorithm. And this was promoted to a mathematical theory in 2007 by Enal, and before that, there were a lot of work by many people. You can think of it as an algorithm that you can just take your favorite software like Sage or Mathematica or whatever you want to use, and then you just write it down explicitly, and then whenever you have a spectral curve, you run the algorithm, and then you get an infinite list of numbers out of it. So basically, you want to generate these omega GNs, starting from the data of omega 0,1 and omega 0,2. So when you see these two indices, the first and the second, the first stands for the genus, and the second stands for the number of mark points. So omega 0,1 has to be understood as something that has one mark point or one boundary, if you wish, and 0 genus, so it's just a disk. And then 0,2 can be thought as the data on the cylinder, right? And then you glue them together in all possible ways. With the help of this K that you see here, that is often referred to as the recursion kernel. And then you build up all the omega GNs. They are multidifferentials on the n copies of the spectral curve, which I will define in a bit. And then you expand them near some particular point, you get some numbers. These are the numbers that you care about. This would be the integrals over the modular space of curves. And it's called recursion because it goes in layers in 2g minus 2 plus n. So you start with omega 0,1 and omega 0,2, and the first guy that you compute is omega 0,3. So the data on a pair of pens. And then you compute omega 1,1 and omega 0,4 that correspond to the next layer, and so on. All right, so I would like to define ENT as the class of all the enumerative problems that are generated by topological recursion. And this class has been continuously expanding since 2007. And it involves many things, as you can see here: mirror symmetry, string theory, WKB analysis, Paleve equation, polynomial invariance of knots, Hitchin systems, and more. All right. So let's dive into the definition of topological recursion. This is a spectral curve for me. So C is a Riemann surface. X and Y are two meromorphic functions in it, such that the critical points are distant. And then moreover, we assume that X has only simple critical points. There is a generalization, but the formula is already complicated enough just with this assumption. And then if you consider a simple critical point, alpha, so such that the x of alpha is 0, because it's simple, it defines a local involution sigma alpha in the vicinity of that point. And then you also need omega 0,2, that is part of the initial data. That is a symmetric bidifferential defined on the topological product of this Riemann surface. And then you want to define the k that you've seen before in the picture. You basically take omega 0,2 and then you integrate. Here you see the alpha appearing. So the recursion kernel is defined in the vicinity of a critical point. And then you divide by this omega 0,1, which is just y dx. And then after you have these ingredients, you can define all the omega gns that you like that. So you suppose that you have all the ones before in layers in the 2g minus 2 plus n, so the Euler characteristic of the surface. And then you want to define the next one. The next one is omega g n plus 1. And then you sum over all the simple branch points. And then you take the residue of z at that point. And then you use the recursion kernel in the vicinity of that point. And then you just take the product of omega g minus 1 n plus 2. And in the 2 points that you're gluing, you put z and the involution of z, and then the rest. And then you sum over all possibilities of splitting the mark points and the genus. And then you take byproducts of the omega gns. And if you check all the omega gns that are involved in this formula, have a higher Euler characteristic. So it's actually a recursion. And yes, you see that Z1 has a totally non-symmetric role in this formula, right? Here we only have Z2, Zn. So it's a very legitimate question to ask whether this formula is symmetric in the Zi's, but it turns out that it is. And the circle upstairs just means that you don't want omega 0,1 in this formula. So let's go back to the drawing. So here I'm computing omega gn plus 1. I attach to the recursion kernel either the surface that has one less genus and 2 more mark points. The genus extra is created by this by gluing the 2 boundaries like that. Here I put z, here I put the involution of z. And then there is only another possible case. It's when the surface that you attach is not connected, because you have 2 disconnected components, and then you just split in all possible ways. So in a sense, it's a very natural formula. All right, so let's give some examples, because you could ask, like, why would I want to do this at all? So, okay, sorry. The examples are in the next slides. I first would like to mention some advantages. The first is that you can write it down and compute with it. The second one, as I already mentioned, is that if you don't need a matrix model for it to work, but if you have a matrix model, you derive the spectral curve and then run the algorithm. It's universal in the sense that very different problems in enumerative geometry are run with topological recursion, just the same exact formula for very different enumerative problems. This is part of the magic. And then it gives you automatically built in the procedure the numbers as the integrals over MGM bar of some cohomology class. So there's a theorem that says that all the omega gns for every spectral curve, they arise as sum of integrals of the MGM bar. And here you have this CGN. It's some class in the cohomology. If you know more about it, it's a cohomological field theory, means that it's a collection of classes that behave very well with each other under the natural maps of the modular space of curves. And here you have some psi classes in the intersection, and then just some auxiliary function xi's, which are basically the integral over omega 0 2. You can think of them like that. And then it does give rise to factorially divergent series. So as in the lecture of Professor Marino yesterday, whenever you see a factorially divergent series, you might think of resurgence. And actually there is more evidence than that. That's every problem that is generated by topological recursion actually is resurgent, but this is not proved, and people has been so far proving it case by case, or are proving it case by case, because there are not many cases proved actually so far. So about examples, this was the first example, and also the more fundamental for a series of reasons. It is about the Witten-Kontsevich numbers. So there was a big conjecture in '91 by Witten that was solved in the PhD thesis of Maxim Kontsevich, that if you consider these integrals of MGM bar of just the psi classes, so in the picture in the slide which was above, here there was a CGN, this cohomological field theory, and now you are taking it to be 1. So this is the simplest possible integral you can have. The partition function of these numbers is a tau function of the KDB hierarchy. This was Witten conjecture. And actually it turns out that if you take the simplest possible spectral curve, that is the Riemann surface to be just a sphere, X has to have some critical points. So you have to take at least Z squared, right? So you have one simple branch Y. This is the simplest X that you can have. And this is the simplest Y that you can have, just the identity. And this is also the simplest omega 0 2 that you can have. So the simplest possible spectral curve gives you the simplest possible cohomology class, which is just 1. For each G and N is just 1. And so the omega GNs, after you expand them, you find exactly these numbers up to some double factorial normalization. So this is the most fundamental example. And then there is another example. You can generate the Weil-Peterson volumes, and this gave a new proof of Miyazakani recursion just by taking Y equal to the sign. So it's very appealing, right? It's the same formula. You just change a little bit the initial data. You get very interesting enumerative problems. And then lately, there was a work that was mentioned also in the last talk about Witten and Stanford about JT gravity. And they deal with super Weil-Peterson volumes. And then it turns out that this is very recent. This is last 2020 by Norbury. That if you Y, instead you put it as the cosine divided by Z, because this has to be odd, then you get exactly the, you get exactly the volumes of the moduli space of the hyperbolic structures on super Riemann surfaces. And the only difference is that you have to insert this theta GN, which is known as the Norbury cohomological field theory. And yeah, so these were the 3 examples that I wanted to bring, and now there will be the original example in which I worked on. So this example is the Maservich volumes, which is something very interesting for the community of flat surfaces. So basically, you can think of Maservich volumes as the properly renormalized volumes of the cotangent bundle of MGM bar. So there is a, first you have to identify the Teichmüller space to the bundle of holomorphic integrable quadratic differential on the puncture surface that at most has simple poles. And then you have a notion of area, so you can restrict yourself to the differentials that have area 1. And it turns out that there is a very nice measure. This was defined by Mazur and Vich. And if you take the total mass of this space, it's finite. So this was the theorem of Mazur and Vich independently. And now, because it's finite, you can compute it, or you can try to compute it. And after you normalize by some powers of pi, these are the numbers that you get for the genus and number of mark points. These are the first numbers. So, yeah, they satisfy topological recursion. This is the main, this is the main theorem, as you might expect. But first, people define some Maservich polynomials. So you have this V omega GNs, and that depends on some variables at 1 and n. And you define them as sum over stable graphs, and then you just normalize one over the automorphism group, and then you take the Laplace transform, and on every edge you put this function over here, and on every vertex of the graph you put this contribution. What is this contribution with many indices? Well, it's just the Witten-Kontsevich numbers. So you just take the integral over the genus of that vertex and the number and the valency of that vertex. And here you put just exponential of some of the variables that you have attached on the leaves and psi classes. So here you have Witten-Kontsevich numbers, but you also decorate the edges like that, and you take Laplace transform. This is the definition of Maservich polynomials. And because you see the dimension of this is finite, it's just 3g minus 3 plus n, and then you collect the contribution on all the vertices. So the final result will also be polynomial in the LIs and also of total degree 3g minus 3 plus n. And then the theorem that was shown before is that up to some normalization, if you take the constant term of this polynomial, these are the Maservich volumes. Okay, so our theorem is that if you take this spectral curve, do you remember, it's very, very similar to the Witten-Kontsevich, and this is not surprising because, well, the vertices are decorated with Witten-Kontsevich numbers. So you still take pi1, just a sphere, and then you take x to be the parabola like before, and y you take minus the identity. But now on the omega 02, you take something different. You take the canonical omega 02, which is this, and then you add to it some extra piece. And this is known as a generalization of the Riemann zeta function. It's called the Hurwitz Riemann zeta function. And then the theorem is that after you run topological recursion, you obtain the omega gns. The first statement is that you can expand the omega gns into Hurwitz zeta Riemann function. You get some coefficients. And the second statement is that these coefficients are exactly the coefficients of the Maservich polynomials. So if you take these coefficients and you specialize, I mean, you construct a polynomial like that, and then you specialize the LIs to 0, which means the DIs to 0. So if you plug here the DIs to 0, you get the Maservich volume. So Maservich volumes, they belong to ENT, the class of problems generated by topological recursion. And so this is, I specialize the formula of topological recursion for you. So I hope it looks a little bit easier than before. So if you want to compute omega gn here, I call it W just because it's I divided by dx, dz1, dz2, dzn. So we don't have differentials anymore. This z to the 0 comes from the residue. And then you have this Hurwitz Riemann zeta function. And then you have the other pieces. So the first, so the statement is that you can expand it in this zeta. And then you take the numbers. And these numbers give you the Maservich volumes, right? So if you want to compute omega 03, well, then the only thing that, this is the recursion kernel, the only thing that you can attach is a cylinder, right? Because you are building a pair of times. So you just attach the cylinders in all possible ways, swapping the variables. And then after you compute, you get this. The coefficient in front of this is 1. And after the normalization that you've seen before, you get the Maservich 03 is equal to 4. So this is how you compute it. And then if you want to compute 1, 1, then you can just attach a 0, 2, just one cylinder, but this time you attach it in a way that it produces an extra genus. And this is also what you get. And well, you work with this. After dividing by pi squared, you get the right result from here. And this is just extra coefficients of the polynomials that have some other meaning. And then you can compute omega 04. You see, you attach on one side, you have to attach a cylinder. On the other side, you have to attach a pair of pens, because that's how you build a sphere with 4 boundaries. And then after you compute, indeed, you can expand everything in zetas. And then you just look at this 3 and this 3, and you normalize, you get Maservich volumes. So we computed a lot of numbers, more than they were ever computed with other methods, because topological recursion is faster than computing with simple stable graphs. This was the main advantage. And then we, looking at the numbers and using some interpolation, we made some conjecture about their big, large asymptotics. And also, well, basically, we conjectured that Maservich volumes over here, they up to some prefactor, they are equal to some polynomial in n, plus another polynomial in n, times this guy, which is a binomial coefficient. And so these are P and Q, and these are the first value for P and Q, such as polynomials. And then we also did the same work for the Ziegeltich volumes. which are related to the Lyapunov exponent that Rafael was mentioning before. And here we have this P star and Q star, just polynomials. And then shortly after, someone proved our conjecture using this IPhT, which is called Kyoto classes. The construction is a little bit technical from algebraic geometry, but I would just like you to look at this theorem, Kyoto formula, that says that you want to compute the Chern character of this virtual bundle over here. And the answer is that the nth Chern character is just equal to some Bernoulli polynomial times the Mumford class minus some other Bernoulli polynomial times the psi classes. And then you have again Bernoulli polynomials. And here you have the boundary map in the model space of curves that produce an edge. This is just producing an edge. And then you decorate the two sides of the edge with psi classes. So now you take this CM over here and you plug it into this exponent and you normalize like that. This is how you usually build total Chern classes, right? But this is not an actual bundle, so it's not going to be a total Chern class, but you kind of pretend that it behaves like that. And then you have these parameters R and S, which are very important. But if you are used a little bit to model space of curves and Mumford formula, you would recognize that if you plug R equal to 1 and S equal to 1 from this formula, and just look at what you get here, the Bernoulli polynomials, all of a sudden, they specialize to the Bernoulli numbers, and you get the Hodge bundle by Mumford formula. So Kyoto formula is some cohomological field theory with a complicated formula that is a generalization of the Hodge bundle.
Sorry, Danilo, just let's negotiate the timing.
Right. Okay, I will quickly move to the end then. Sorry. So this is the spectral curve that produces the integrals of Kyoto class. And then the way they proved our conjecture is to express Mazurich volumes as integral of Kyoto class. And now we thought, aha, we know the spectral curve that generates Kyoto class. So we found a second spectral curve, this proposition over here. So if you take, again, CP1, but now X is more complicated with this log over here, and Y is Y squared, and omega 02 is just the usual Bernoulli kernel. You run the topological recursion with this, and you again get the Mazurich volume. So this is a second spectral curve for the same problem. And then there has been like many follow-ups about integrable hierarchies because of this. And yeah, so this was the main result. But I just wanted basically to convince you that topological recursion is a universal procedure that generates many different enumerative geometric problems. And if you have a matrix model, you might want to look at the spectral curve, and then if the spectral curve is nice enough, you can use this procedure and generate a lot of numbers. So why people think that there is resurgence behind the class of enumerative problems generated by T? Because if you take this symplectic invariance Fg as the residue of omega G1 with the primitive of the 0, 1, they give a factorially divergent series with a Gevrey index that has been shown to be at most 5, but it's likely 2. And then there is a theory of generalized cycle by NR that suggests that it's going to be the case in general. So there are many work in progress about resurgence and topological recursion, but now I'm out of time. So I would like instead to, in 30 seconds, to mention that we are organizing the ERC Synergy conference in the south of Italy. As you can see, it's a nice place, and it's going to be in September. We structured in a way that there will be 4 days of basic courses on topological recursion. So just starting from the very definition of topological recursion, 4 days of advanced courses on related topics, and then 4 days only for experts working in topological recursion and resurgence, or resurgence, just to collaborate. So it will be a very open workshop without many talks at all. You can already subscribe to any of the 3 parts independently, but okay, there are some requirements. But you can already go on the website and subscribe if you wish.
All right, so thanks a lot, Danilo.